blue marble, as we affectionately call our home, floats through the vast, cold expanse of space, a vibrant beacon of life. When viewed from orbit, it is a breathtaking spectacle. Swirling white clouds dance above deep azure oceans that cover more than 2/3 of its surface, punctuated by the greens and browns of continents. This is a planet teeming with biodiversity, from the microscopic organisms in the deepest trenches to the towering forests and sprawling metropolises. It is a world defined by liquid water, the essential solvent and cradle for all known life, cycling ceaselessly from oceans to atmosphere to land, shaping landscapes and sustaining ecosystems. We experience its rhythms daily: the gentle warmth of the sun, the refreshing rain, the predictable march of seasons. This dynamic, comfortable world feels incredibly stable, a constant in our human experience, a testament to billions of years of intricate geological and biological evolution. It is a place of profound familiarity, the only home any of us has ever known. But what if this image, so deeply ingrained in our collective consciousness, is merely a snapshot in a much longer, far more dramatic story? What if, in the distant annals of its history, our planet underwent a transformation so radical, so utterly alien, that it would be almost unrecognizable to us today? Imagine for a moment that familiar blue sphere slowly, inexorably, beginning to change. The vibrant blues of the ocean start to dull, then lighten, as vast expanses of ice begin to form, creeping inwards from the poles. The verdant greens of the land are gradually swallowed by a blinding white blanket. The swirling clouds become denser, reflecting more and more of the sun's light back into space. The temperatures plummet, not just in the polar regions, but globally, extending to the very equator. This is not a fleeting ice age, not merely a period of colder weather, but a cataclysmic deep freeze that encased the entire globe, turning the dynamic, living Earth into a gigantic, silent snowball. This astonishing concept, known to scientists as Snowball Earth, describes a period hundreds of millions of years ago when our planet was, for all intents and purposes, a solid ball of ice. Picture it: a world where oceans, in some places, were buried under sheets of ice several kilometers thick, more than twice the height of Mount Everest if you stacked it from the ocean floor. The surface would have been an unbroken expanse of white, stretching further than the eye could see, under a perpetual, dim sunlight that struggled to penetrate the reflective crust. The familiar sounds of crashing waves, rushing rivers, and rustling leaves would have been replaced by an eerie, profound silence, broken perhaps only by the groaning and cracking of the immense ice sheets themselves. It is a vision that stands in stark contrast to everything we understand about our life-sustaining planet, presenting a profound mystery that has captivated geologists, climatologists, and biologists for decades. To truly grasp the scale of this transformation, we need to travel back in time, not just thousands or millions of years, but deep into the Proterozoic Eon, a period spanning from about 2.5 billion to 541 million years ago. Specifically, the most extreme snowball Earth events occurred during a period known as the Neoproterozoic era, roughly between 720 and 635 million years ago. These weren't isolated incidents, but a series of at least 2, possibly 4, global glaciations, each lasting for millions of years. For context, the dinosaurs appeared much later, around 230 million years ago, and modern humans are a mere blink in geological time, emerging only a few 100,000 years ago. So we are talking about an epoch so ancient that the continents we recognize today had not yet fully formed, and the complex animal life we see all around us had yet to evolve. The life forms that existed then were primarily single-celled organisms, simple multicellular algae, and early forms of sponges, existing in oceans that would become utterly transformed. The scientific journey to uncover this frozen past began with a series of perplexing geological observations. Geologists studying ancient rock formations in places as diverse as Australia, Namibia, and Canada found unmistakable evidence of glacial activity. Rocks scarred by the movement of ice sheets and sedimentary deposits known as tillites, which are characteristic of glacial debris. What made these findings so remarkable was their location. Many of these glacial deposits were found in rocks that, based on paleomagnetic evidence, were formed near the equator. Imagine finding evidence of massive glaciers in what was once a tropical region, a place that today experiences scorching heat. This was a direct contradiction to the prevailing understanding of Earth's climate history, which assumed that glaciers were confined to polar regions as they are today. How could glaciers exist, let alone thrive, in what was then the tropics? This geographical paradox was a powerful clue, suggesting a climate event far more extreme than any previously imagined. This radical idea initially met with skepticism, as any groundbreaking theory often does. The notion of a completely frozen Earth seemed to defy common sense and basic physics. How could life survive such an ordeal? And how could such a frozen world ever thaw? Yet, as more evidence accumulated, from distinctive cap carbonates found immediately above glacial deposits, suggesting a rapid chemical change after the melt, to geochemical signatures in ancient sediments, the Snowball Earth hypothesis gained significant traction. It transformed from a fringe idea into a central pillar of Neoproterozoic geology and climate science. It painted a picture of a planet that was not merely cold, but utterly besieged by ice, a planetary body that pushed the very limits of habitability. Consider the sheer audacity of this concept. Our planet, which we know as the vibrant blue marble, was once a brilliant white, reflecting so much sunlight that it would have appeared as a dazzling, almost sterile gem in the cosmos. It was a world where photosynthesis, the fundamental process that underpins most of Earth's ecosystems by converting sunlight into energy, would have been drastically curtailed or even ceased across vast areas. Imagine the challenges this would have posed for the simple life forms existing at the time. Yet somehow, life persevered. It found refugia, pockets of warmth and liquid water, perhaps near hydrothermal vents on the ocean floor, or in thin, sunlit cracks within the ice itself. This survival against such impossible odds is perhaps as profound a mystery as the glaciation itself. So this is the grand paradox we embark upon. How did our life-sustaining planet, a world destined to become home to complex animals and eventually intelligent beings, transform into such a hostile, frozen wasteland? What chain of events could have initiated such a catastrophic climatic shift, pushing Earth to the very brink of complete biological annihilation? And perhaps even more astonishingly, what mighty forces could have eventually broken this icy grip, allowing our world to thaw, to breathe again, and ultimately to flourish with an explosion of new life? These questions don't just explore an ancient chapter of Earth's story. They offer profound insights into the delicate balance of our planet's climate system, its incredible resilience, and the interconnectedness of geology, atmosphere, and life. Let us journey back then to this alien past to uncover the epic tale of the Snowball Earth, Our journey into Earth's deep past has introduced us to a planet dramatically different from the one we know. A world almost entirely encased in ice. But how did this transformation occur? What forces could possibly drive our vibrant, water-rich planet to such an extreme state? The story of Snowball Earth is not one of a sudden catastrophe, but rather a slow, inexorable descent, triggered by a series of interconnected geological and atmospheric events that began hundreds of millions of years ago, during a span of time geologists call the Neoproterozoic era, roughly between 717 and 635 million years ago. At the heart of this climatic unraveling was a fundamental shift in Earth's atmospheric composition, specifically a significant reduction in the amount of carbon dioxide, or CO2, a gas that plays a crucial role in regulating our planet's temperature. Think of carbon dioxide as Earth's natural thermostat, or perhaps a cozy blanket in its atmosphere. It's a greenhouse gas, meaning it traps some of the sun's outgoing heat, preventing it from radiating back into space and keeping the planet warm enough to sustain liquid water and, consequently, life. Without a sufficient amount of this atmospheric blanket, Earth's average temperature would plummet dramatically. And that is precisely what happened. For reasons we're about to explore, the carbon dioxide levels in Earth's ancient atmosphere began to fall, thinning this protective blanket and allowing more heat to escape. The primary culprit behind this atmospheric thinning was a process known as silicate weathering. While it might sound technical, it's actually a natural, continuous geological process that has profoundly shaped our planet over eons. Imagine rain falling on rocks. This rainwater, slightly acidic from dissolved atmospheric carbon dioxide, chemically reacts with the silicate minerals that make up much of Earth's crust. During this reaction, atmospheric CO2 is drawn out of the air and combines with water and rock minerals to form new compounds, primarily bicarbonate ions and silica. These dissolved substances are then carried by rivers to the oceans, where they can eventually settle out as carbonate sediments or be incorporated into the shells and skeletons of marine organisms. In essence, silicate weathering acts as a giant, slow-motion carbon sink, continuously pulling carbon dioxide from the atmosphere and locking it away in rocks and ocean sediments. It's a vital long-term regulator of Earth's climate, but its speed can vary dramatically. During the Neoproterozoic, a unique arrangement of continental landmasses significantly accelerated this process. At that time, much of Earth's land was consolidated into a massive supercontinent known as Rodinia. This sprawling landmass was largely situated in the tropical and equatorial regions of the planet. Now, consider what happens when vast expanses of land are located in warm, humid zones. The conditions are ripe for enhanced weathering. Tropical climates are characterized by abundant rainfall and higher temperatures. Water is the primary agent for chemical weathering, and warmer temperatures speed up chemical reactions considerably. So heavy tropical rains, falling on exposed silicate rocks across a huge continent near the equator, would have dissolved those rocks at an exceptionally rapid rate. This increased chemical erosion would have exposed fresh rock surfaces to the atmosphere, providing an endless supply of new material for the weathering process to consume. Furthermore, the breakup of Rodinia, which began around 750 million years ago, likely exacerbated this effect. As the supercontinent fragmented, it created numerous smaller continental blocks and rifting zones. These rifting events often lead to the formation of new mountain ranges and expose vast amounts of fresh rock to the atmosphere, accelerating weathering even further. The newly formed coastlines also meant more shallow seas, which could foster increased biological productivity, leading to more carbon burial in marine sediments. So, the very architecture of Earth's surface, the arrangement of its land masses, became an unwitting accomplice in the planet's cooling, acting like a giant vacuum cleaner for atmospheric carbon dioxide. This continental configuration also had profound implications for ocean currents. As land masses shift, they reshape ocean basins, redirecting the massive flows of water that distribute heat around the globe. While the precise details of Neoproterozoic ocean currents are complex and subject to ongoing research, it is plausible that these reconfigurations could have led to less efficient heat transport from the equator towards the poles, contributing to a general cooling trend. Moreover, certain continental arrangements might have promoted oceanic upwelling, bringing nutrient-rich waters to the surface. This could have fueled bursts of marine life, which, upon death, would sink to the ocean floor, carrying their carbon-rich organic matter with them and further sequestering carbon dioxide from the atmosphere. So, the shifting continents didn't just enhance weathering, they might have also altered the ocean's capacity to store carbon, all contributing to the diminishing atmospheric CO2 blanket. As the atmospheric carbon dioxide levels continued their downward spiral, Earth's global temperature began to steadily drop. The planet, slowly losing its atmospheric insulation, started to cool. This initial cooling, however, was merely the prelude to a much more dramatic and self-reinforcing process, what scientists call a positive feedback loop. In this context, it refers to a situation where a change in one direction triggers further changes that amplify the original effect, creating a runaway scenario. For Snowball Earth, this feedback loop was driven by ice itself, specifically its reflectivity, a property known as albedo. Imagine looking at our planet from space. You see vast blue oceans, green and brown land masses, and swirls of white clouds. The dark oceans and land absorb a significant portion of the incoming sunlight, converting that energy into heat, which warms the planet. Clouds, on the other hand, reflect some sunlight back into space, but nothing reflects sunlight quite as efficiently as fresh white ice and snow. These surfaces boast a very high albedo, meaning they bounce a large percentage of solar radiation directly back into space, rather than absorbing it. So, here's how the positive feedback loop began its relentless grip. As global temperatures cooled due to reduced CO2, glaciers and ice sheets started to expand from the polar regions and high-altitude areas. Picture small patches of white appearing at the very top and bottom of our globe, gradually growing larger. Each new patch of ice, being bright and reflective, immediately began to reflect more of the sun's energy away from Earth. Less absorbed solar energy meant the planet became even colder. This further cooling, in turn, allowed even more ice to form and expand, creeping further away from the poles and towards the equator. This created a vicious cycle. More ice leads to more reflection, which leads to more cooling, which leads to more ice. It's like a mirror growing larger and larger, reflecting more and more of the sun's warmth away, leaving the planet increasingly shrouded in cold. This process wasn't gradual indefinitely. There appears to be a critical tipping point. Once the expanding ice sheets reached a certain latitude, perhaps around 30 degrees north or south, roughly the latitude of regions like Florida or Egypt today, the feedback became unstoppable. At this point, so much of the Earth's surface was covered by reflective ice that the planet simply couldn't absorb enough solar energy to halt the spread. The albedo feedback mechanism took over completely, propelling Earth towards a full-blown global glaciation. The speed of this expansion would have been terrifying if there had been complex life forms to witness it. From the poles, the ice fronts would have marched relentlessly towards the equator, perhaps at rates of meters per day, transforming dark, heat-absorbing oceans and continents into vast, blindingly white expanses. The atmosphere, already thin of its greenhouse gases, would grow colder and drier, stripped of much of its moisture as precipitation fell primarily as snow and was locked away in the growing ice sheets. The very clouds, themselves reflective, would have diminished as the hydrological cycle slowed down dramatically under freezing conditions. It wasn't just a slow chill. It was an accelerating plunge into an icy abyss, driven by the planet's own reflectivity. Imagine the oceans, once teeming with early microbial life, slowly succumbing to the cold. First, a thin skin of sea ice would form, expanding outward from the coasts and from higher latitudes. This initial ice would be relatively thin, perhaps a few meters thick, but as it expanded, it would contribute its own powerful reflectivity to the albedo feedback, further accelerating the cooling. Over millions of years, this process continued, until eventually, even the equatorial oceans began to freeze. The prevailing scientific models suggest that the ice cover would have become immense, reaching depths of several kilometers in places, effectively encasing the entire globe in a colossal, gleaming white shell. This wasn't just a thick layer of ice at the poles, as we see today. This was a planet where ice dominated every landscape from pole to pole. The once familiar blue marble would have been transformed into a brilliant white sphere, reflecting so much sunlight that it would have appeared as a dazzling beacon in space. The sheer scale of this transformation is difficult to grasp. Picture a world where the average global temperature plummeted to perhaps minus 50 degrees Celsius or even lower. The air would be thin, dry, and bitterly cold, with very little atmospheric moisture to create clouds or precipitation cycles as we know them. The vibrant blues of the ocean would be replaced by the sterile white of an unbroken ice sheet, stretching as far as the eye could see, broken only perhaps by the occasional volcanic peak piercing through the frozen crust. The landmasses, too, would have been buried under immense glaciers, scouring the bedrock and leaving behind telltale geological signatures that scientists would later uncover hundreds of millions of years later. These immense ice sheets would have been kilometers thick, exerting enormous pressure on the continental crust beneath them. The world would have been eerily silent, devoid of the rushing rivers, crashing waves, and rustling winds that characterize our modern active planet. The hydrological cycle, the continuous movement of water on, above, and below the surface of the Earth, would have largely ground to a halt, with most of the planet's free water locked away in glacial ice. So the story of Earth's descent into a snowball state is a complex interplay of forces. It began with the slow, steady removal of carbon dioxide from the atmosphere by enhanced silicate weathering, a process amplified by the specific arrangement of continents in the tropical belt. This reduction in Earth's atmospheric blanket led to an initial cooling. Then, crucially, the planet's own reflectivity, its albedo, took over. As ice sheets grew, they reflected more and more sunlight, causing further cooling and accelerating the expansion of ice in a powerful, self-reinforcing feedback loop. This runaway process ultimately transformed our familiar blue marble into a dazzling, frigid white world, setting the stage for one of the most extreme climatic events in Earth's long history. The planet was now locked in an icy embrace, seemingly without any hope of escape, a testament to the powerful, sometimes unforgiving feedback mechanisms that govern planetary climate. Imagine standing on the surface of this colossal frozen Earth nearly 700 million years ago. The vibrant blues and greens we associate with our planet today would be utterly absent. Instead, a stark, blinding white stretches in every direction, an endless expanse of ice reflecting the faint sunlight back into the void of space. The air itself would be thin, dry, and brutally cold, perhaps dropping to temperatures as low as -50 degrees Celsius, even at the equator. This was not merely a polar ice cap. This was a global shroud, an unbroken shell of ice encasing the entire world from pole to pole. Beneath this frozen crust, the oceans, once teeming with life and dynamic currents, lay entombed. Scientists estimate that the ice covering these ancient seas could have been several kilometers thick, perhaps reaching depths of 3 to 5 kilometers in places, particularly over the deepest parts of the ocean basins. To put that into perspective, imagine a wall of ice taller than Mount Everest, not as a single peak, but as a continuous undulating ceiling stretching across vast oceanic expanses. This immense weight pressed down on the water below, creating an environment of unimaginable pressure and perpetual darkness. The sheer scale of this ice cover had profound consequences. One of the most fundamental planetary processes, the hydrological cycle, essentially ground to a halt. Normally, water evaporates from the oceans, forms clouds, falls as rain or snow, and eventually flows back to the sea, driven by the sun's energy. But with the entire ocean surface sealed off by kilometers of ice, evaporation ceased almost entirely. No more clouds formed from the oceans, no more rain fell to nourish land masses, and no rivers carved their paths across the continents. The atmosphere became extraordinarily dry, perhaps only carrying trace amounts of water vapor released from volcanic activity or sublimating ice. The familiar sounds of our planet, the crashing of waves against a shoreline, the rush of a waterfall, the gentle patter of rain, would have been utterly silenced. A profound stillness would have enveloped the globe, broken only by the occasional creak and groan of the colossal ice sheet adjusting to tectonic stresses, or perhaps the distant rumble of a subglacial earthquake. Within this suffocating embrace of ice, the vast volumes of ocean water that remained liquid beneath the frozen lid became isolated from the atmosphere and from sunlight. Without surface winds to churn the water and introduce oxygen, and without photosynthetic organisms to produce oxygen, the deep oceans likely became largely anoxic, devoid of free oxygen. This would have transformed the chemistry of the seawater, allowing iron and other metals to dissolve in much higher concentrations than they do today, turning the deep ocean into a vast, dark, chemical soup. The once vibrant global ocean currents, driven by temperature and salinity differences, would have ceased their grand circulation, leaving the subglacial waters largely stagnant, a realm of slow, inexorable chemical change. So, what became of life during this epochal deep freeze? Before the Snowball Earth events, life was predominantly microbial, consisting of single-celled bacteria and archaea, along with some early, relatively simple multicellular algae and protozoa. These organisms were accustomed to living in sunlit surface waters or shallow marine environments. The sudden, dramatic shift to a planet encased in ice presented an existential crisis. Most surface-dwelling life dependent on sunlight for photosynthesis would have perished. The fossil record from this period shows a distinct lull, a bottleneck where biodiversity plummeted. Yet, life is remarkably tenacious. a testament to its incredible adaptability. Scientists believe that certain forms of life managed to survive in isolated refugia, small, protected pockets, where conditions were less extreme. One of the most compelling candidates for such havens are hydrothermal vents, often called black smokers or white smokers, in modern oceans. These are cracks in the seafloor where superheated mineral-rich water, warmed by magma chambers deep within the Earth's crust, spews out into the cold ocean. Today, these vents support bizarre and vibrant ecosystems, entirely independent of sunlight, based on chemosynthesis, a process where microbes derive energy from chemical reactions rather than light. Imagine these vents during Snowball Earth, tiny oases of warmth and chemical energy, glowing faintly in the abyssal darkness beneath kilometers of ice. Here, specialized bacteria and archaea could have thrived, forming the base of a food web that included worms, crustaceans, and other invertebrates. These communities would have been isolated, scattered across the vast, dark ocean floor, but they represented a lifeline, a biological spark waiting for the planet to thaw. The constant heat from the Earth's interior would have kept the water around these vents liquid, even as the global ocean above them was frozen solid. The chemical nutrients, such as hydrogen, sulfide, and methane, continuously supplied by the vents, would have fueled these unique ecosystems, ensuring the persistence of at least some forms of life through the long, frozen aeons. Another potential refuge could have been subglacial lakes, similar to those discovered beneath the vast ice sheets of Antarctica today, such as Lake Vostok. These lakes are kept liquid by geothermal heat radiating from the Earth's interior and by the immense pressure of the overlying ice, which lowers the freezing point of water. While light would have been virtually non-existent, these lakes could have harbored chemosynthetic microbial communities, perhaps even organisms adapted to extremely low nutrient levels, surviving on whatever dissolved minerals or organic matter managed to accumulate. Such environments would have been profoundly isolated, cut off from the global oceanic system, evolving in their own unique ways, but crucially, preserving life's blueprint. There is also the slush ball hypothesis, a nuanced alternative to the hard snowball model, which posits that the ice cover might not have been entirely continuous. Under this scenario, a thin band of open water or highly saline slush might have persisted near the equator, where the sun's rays were strongest. If such unfrozen patches existed, they would have been extremely harsh environments, cold, perhaps hypersaline due to evaporation, and brine rejection from freezing ice, and subject to intense ultraviolet radiation in the thin atmosphere. Yet, even here, some photosynthetic microbes might have clung to existence, perhaps forming mats in shallow protected melt ponds, or within the ice itself, utilizing whatever meager sunlight penetrated the atmospheric haze. These locations would have been incredibly rare, small refuges in a world otherwise utterly hostile to complex life. For hundreds of millions of years, Earth remained in this frozen state. Imagine the sheer duration, a period longer than the entire reign of the dinosaurs. But instead of dynamic ecosystems and evolving creatures, it was a time of geological stasis and biological dormancy for much of the planet. Life, reduced to its most resilient forms, endured in these scattered, hidden pockets, a fragile flame flickering in the universal darkness. The planet had become a giant, silent mausoleum, but within its icy tomb, the seeds of future complexity were patiently waiting for the inevitable thaw. The very processes that had led to this global glaciation were also paradoxically setting the stage for its eventual reversal a slow but unstoppable geological clock ticking beneath the frozen surface. Imagine a world frozen solid, encased in an armor of ice several kilometers thick, stretching from pole to pole. The familiar blue marble transformed into a stark white sphere, spinning silently through the cosmos. For millions of years, this was Earth's reality. Life, if it persisted, did so in hidden pockets, under immense pressure, or around the faint glow of geothermal vents deep beneath the suffocating ice. The very processes that usually regulate our planet's climate, the intricate dance of the carbon cycle, have been brought to a grinding halt on the surface. Yet, even in this profound stasis, a powerful, relentless force was at work beneath the surface. An engine of planetary resuscitation slowly but surely preparing for the great thaw. To understand how Earth escaped its icy prison, we must first revisit the planet's fundamental thermostat, carbon dioxide, or CO2. In our modern world, and for much of Earth's history, the atmosphere's CO2 levels are regulated by a complex interplay of geological and biological processes. One crucial mechanism is silicate weathering. When rainwater, slightly acidic from dissolved atmospheric CO2, falls on silicate rocks, it slowly dissolves them in a chemical reaction. This process draws CO2 out of the atmosphere, transforming it into bicarbonate ions that are eventually carried by rivers to the oceans. There, marine organisms use these ions to build shells, and ultimately, the carbon is sequestered in carbonate sediments on the sea floor, effectively locking away atmospheric CO2 for geological timescales. This mechanism acts as a long-term cooling feedback, preventing CO2 from accumulating indefinitely. But during the Snowball Earth epoch, this vital regulatory system was largely incapacitated. With the continents and oceans entombed beneath an immense, reflective crust of ice, the primary pathways for atmospheric CO2 removal were blocked. There was no exposed land for rainwater to weather silicate rocks. The vast, frozen oceans could no longer absorb CO2 directly from the atmosphere or host the marine life that would typically incorporate it into sediments. The planet's great carbon sink had been plugged. The removal side of the atmospheric CO2 equation had essentially vanished. However, the Earth's internal engine never sleeps. Deep beneath the kilometers of ice, the planet's molten core continued to churn, driving tectonic plates and fueling volcanic activity. Volcanoes, whether erupting violently through the ice in isolated dramatic events, or, more commonly, silently spewing gases along mid-ocean ridges and subduction zones, continued their inexorable release of carbon dioxide. This CO2, along with other gases like water vapor and sulfur dioxide, originates from the Earth's mantle and crust, released through fissures and vents in the planet's crust. It is a constant geological exhale, a fundamental part of Earth's deep carbon cycle. During the Snowball period, this volcanic outgassing persisted, unimpeded by the surface conditions. Imagine the planet as a vast, sealed pressure cooker. The heat source, the Earth's internal furnace, continues to generate steam. In this analogy, CO2. But the usual vent, the silicate weathering process, is blocked. Over millions of years, this seemingly small, steady trickle of volcanic CO2 began to accumulate in the atmosphere. Each eruption, each plume of gas rising from a deep-sea vent, added infinitesimally to the growing blanket of greenhouse gases. The pace of this accumulation was incredibly slow by human standards, spanning perhaps 10 to 15 million years for each major snowball event. This wasn't a sudden burst. It was a relentless, geological drip, 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 patiently building up the conditions for release. As the millennia turned into eons, the atmospheric concentration of carbon dioxide swelled to unprecedented levels. Scientists estimate that CO2 levels may have reached concentrations hundreds, or even thousands, of times higher than today's approximately 420 parts per million. To put that into perspective, imagine an atmosphere so thick with CO2 that it would be like breathing the air in a tightly sealed, heavily polluted industrial space, but on a planetary scale. This was a super greenhouse effect in the making, a powerful thermal blanket woven by geological processes. The atmosphere, once thin and cold, was slowly becoming a dense, heat-trapping envelope. Even though the planet's surface remained a gleaming white mirror, reflecting the vast majority of incoming solar radiation back into space, the sheer potency of this CO2-rich atmosphere began to make a difference. The trapped infrared radiation, the heat trying to escape from Earth, found itself increasingly unable to penetrate this atmospheric barrier. The air itself began to warm, slowly at first, then with increasing intensity. The upper layers of the ice sheets, particularly in the equatorial regions where solar insolation was strongest, would have been the first to feel this subtle, yet persistent warming. The eventual tipping point arrived when the atmospheric warming became sufficient to initiate melting, even on the highly reflective ice surface. This might have begun with small, ephemeral pools forming on the ice surface during brief periods of stronger sunlight, or perhaps with a slight thinning of the ice at its edges. But once the melting started, a powerful and rapid reverse feedback loop kicked in, accelerating the process dramatically. Consider the albedo effect once more. Albedo refers to how much sunlight a surface reflects. Bright white ice has a very high albedo, reflecting up to 90% of incoming solar radiation. Dark ocean water, by contrast, has a very low albedo, absorbing more than 90% of sunlight. As the super greenhouse atmosphere warmed the ice sufficiently to create the first patches of open water, even tiny ones, these dark patches absorbed significantly more solar energy. This absorbed heat further warmed the surrounding ice, causing more melting, which exposed more dark water. This was a runaway process, a positive feedback loop now working in reverse, pushing the planet rapidly towards a thaw. Imagine the spectacle: the pristine, unbroken white surface beginning to crack and groan. Rivers of meltwater, dark and turbulent, would have begun carving channels across the ice sheets, rushing towards the newly exposed ocean. Massive icebergs, some perhaps the size of small countries, would carve off the edges of the retreating glaciers, plunging into the frigid waters with thunderous roars that had been unheard for millions of years. The silence of the Snowball Earth would be shattered by the cacophony of a world coming back to life. The sounds of grinding ice, rushing water, and the immense power of geological change. The rate of this global thaw was, in geological terms, incredibly swift. Some models suggest that the entire planet could have transitioned from a frozen state to an ice-free one in as little as a few thousand years, perhaps even less. This is a blink of an eye compared to the millions of years it spent frozen. As the ice retreated, it revealed a landscape utterly transformed. Vast quantities of fresh water, released from the melting glaciers, poured into the oceans, potentially altering ocean salinity and circulation patterns on a global scale. This immense freshwater influx also carried with it an unprecedented load of sediments and dissolved minerals scoured from the newly exposed continental land masses. The atmosphere itself would have undergone a dramatic transformation. With immense amounts of water evaporating from the newly exposed oceans, humidity would have soared, leading to persistent dense cloud cover and intense torrential rainfall. the Earth would have transitioned from a silent, frigid desert to a stormy, humid, and intensely active world. The air would have been thick with water vapor, a powerful greenhouse gas in its own right, further amplifying the warming trend. The initial super greenhouse effect, driven by volcanic CO2, would have been quickly augmented by the release of water vapor, leading to a period of extreme warmth and humidity. This rapid, dramatic shift from a frozen world to a hot, wet one had profound consequences. The oceans, once anoxic and stagnant beneath their icy lid, would begin to reoxygenate as they mixed with the oxygen-rich atmosphere and received nutrient-rich runoff from the land. The sudden availability of vast quantities of nutrients, flushed from millions of years of accumulated rock weathering and volcanic ash, would create an incredibly fertile environment in the newly invigorated oceans. This extreme environmental upheaval, from one of the most hostile planetary states imaginable to a burgeoning hothouse, set the stage for one of the most significant periods in the history of life. The long, patient work of Earth's internal engine, the relentless exhalation of volcanoes, had finally broken the icy grip, preparing the way for a planetary rebirth. Imagine a world reborn from ice, not with a gentle spring, but with a sudden, violent awakening. The long, silent reign of Snowball Earth had finally ended, giving way to a period of intense, almost unimaginable warmth. The vast, reflective ice sheets, which had once bounced most of the sun's energy back into space, were now gone, replaced by dark, heat-absorbing ocean water. This, combined with an atmosphere supersaturated with carbon dioxide, likely hundreds, perhaps even thousands, of times higher than today's levels, transformed our planet into a veritable hothouse. The air itself would have felt thick, humid, and oppressive, a dense blanket trapping every photon of solar energy. Surface ocean temperatures likely soared, reaching averages of 30 to 40 degrees Celsius, turning much of the world's seas into a warm, shallow bath. In tropical regions, temperatures might have climbed even higher, creating steaming near boiling zones. This extreme heat supercharged the planet's hydrological cycle. Evaporation rates from the vast open oceans would have been astronomical, filling the atmosphere with immense quantities of water vapor. The sky would have been a perpetual canvas of churning clouds, often dark and heavy, ready to unleash torrential downpours. Picture the constant sound of rain, not just a gentle shower, but deluges of biblical proportions, drumming incessantly on the newly exposed land masses. Rivers, swollen to unimaginable widths and depths, would have roared across the continents, carving new canyons and reshaping landscapes that had been locked beneath ice for millions of years. The sight would have been one of geological chaos, mudslides, flash floods, and debris-laden torrents rushing towards the sea, carrying with them the accumulated detritus of an entire ice age. This era of extreme warmth and humidity wasn't just a climatic shift. It was a planetary reset, triggering a monumental nutrient flush. For millions of years, while Earth was encased in ice, the normal cycle of weathering and erosion had been largely suspended. Continental rocks, once exposed to the elements, had been shielded by kilometers of ice. Atmospheric carbon dioxide, though accumulating, couldn't be efficiently drawn down by the weathering of silicate rocks because the rocks themselves were inaccessible. However, below the ice, and trapped within it, a vast reservoir of nutrients had been slowly accumulating. Dust from volcanic eruptions, mineral particles ground by glacial movement, and the products of slow chemical reactions under the ice all remained locked away. When the ice finally melted, it was like uncorking a giant bottle. The torrential rains and massive meltwater runoff began to aggressively weather the newly exposed, barren rock surfaces. The super-high atmospheric carbon dioxide dissolved into the rainwater, forming carbonic acid, which further accelerated chemical weathering. Imagine the exposed granite and basalt, having been protected for so long, now rapidly dissolving under this acidic rain and warm conditions. This process released an unprecedented quantity of essential nutrients, phosphates, nitrates, iron, and various trace elements, into the rivers and ultimately into the global oceans. Phosphorus, in particular, is often a limiting nutrient for life in the oceans. Its sudden, massive influx would have acted like a powerful fertilizer for the marine ecosystems. The previously anoxic, oxygen-deprived oceans, which had existed beneath the thick ice sheets, were now being rapidly stirred and oxygenated at the surface due to warmer temperatures and increased primary productivity. This combination of abundant nutrients and rising oxygen levels created an ideal environment for a colossal bloom of photosynthetic organisms like cyanobacteria and early algae in the surface waters. These microscopic life forms, feasting on the nutrient bonanza, would have reproduced at astonishing rates, covering vast stretches of the oceans in a green, soupy film. This initial explosion of primary productivity had profound consequences. While these organisms consumed atmospheric carbon dioxide, they also produced vast amounts of oxygen as a byproduct of photosynthesis. When these organisms died, their organic remains sank to the ocean floor. The sheer volume of this decaying organic matter initially led to a resurgence of anoxic conditions in deeper ocean waters, as bacteria consumed oxygen to decompose the organic material. This created a complex layered ocean chemistry, oxygenated near the surface, but still largely anoxic at depth. However, over geological timescales, the burial of some of this organic carbon in sediments helped to sequester carbon away from the atmosphere, slowly moderating the hothouse effect and permanently adding to the planet's free oxygen budget. The Earth, in essence, was transforming itself. The initial chaos of the melt gave way to a dynamic, evolving environment. Sea levels fluctuated dramatically, first rising rapidly from meltwater, then expanding further as the oceans warmed. Ocean currents, once constricted by ice or entirely different, began to re-establish, redistributing heat and nutrients across the globe. This period of intense environmental change, marked by extreme warmth, high humidity, and a nutrient-rich ocean, set the stage for one of the most remarkable evolutionary events in Earth's history: the Cambrian explosion. For hundreds of millions of years prior to this period, life on Earth had been relatively simple, dominated by single-celled organisms and, more recently, by the Ediacaran biota, a collection of enigmatic, soft-bodied multicellular forms that mostly lay flat on the seafloor, absorbing nutrients from the water. These organisms were largely sessile, meaning they didn't move much, and their flattened form suggested that they relied on a high surface area to absorb scarce oxygen and nutrients, perhaps indicative of an oxygen-limited world. They represented a tentative first step towards multicellularity, but lacked the complexity, mobility, and hard parts that would soon come to define animal life. The connection between the Snowball Earth thaw and the Cambrian explosion, which began around 541 million years ago and lasted for a geologically rapid 13 to 25 million years, is a subject of intense scientific study. Many scientists propose that the extreme environmental changes directly following the Snowball events acted as a powerful evolutionary catalyst. The critical factor was the massive increase in atmospheric and oceanic oxygen levels. Larger, more active and metabolically demanding organisms, such as complex animals with internal organs and muscles, require significantly more oxygen to survive and thrive. The post-Snowball oxygenation, a direct consequence of the massive primary productivity driven by the nutrient flush and the subsequent burial of organic carbon, provided this essential ingredient. Imagine the oceans, once quiet and largely populated by simple forms, now becoming a vibrant, competitive arena. The abundant food source from the algal blooms provided the energy base for increasingly complex food webs. New ecological niches opened up, creating opportunities for organisms to specialize and diversify. It was in this dynamic environment that the Cambrian explosion truly took off. Almost all modern animal phyla, the major divisions of the animal kingdom, made their first appearance in the fossil record during this relatively short geological window. This wasn't just an increase in numbers, it was an explosion of biological innovation. One of the most significant developments was the evolution of hard body parts. Prior to the Cambrian, most organisms were soft-bodied, leaving little fossil evidence. But suddenly, organisms began to develop shells, exoskeletons, and internal skeletons. Think of the iconic trilobites, early arthropods encased in segmented mineralized armor, or the brachiopods, marine animals with bivalve shells. Why this sudden development? Hard parts offered protection against predators, which were also evolving rapidly. They provided structural support, allowing organisms to grow larger and achieve more complex body plans. And they offered attachment points for muscles, facilitating more sophisticated movement. The emergence of eyes was another revolutionary innovation. Once organisms could actively perceive their surroundings, the evolutionary arms race accelerated dramatically. Predators, like the fearsome Anomalocaris, a meter-long apex predator of the Cambrian seas, developed keen eyesight to hunt. Prey animals, in turn, evolved better defenses, camouflage, and escape mechanisms. This constant interplay between predator and prey drove further diversification, creating an intricate web of ecological relationships that continues to shape life on Earth today. We see the rapid development of diverse forms of locomotion. Animals that could actively swim through the water column, burrow into the sea floor, or crawl across its surface. Early chordates, like Picaia, which possessed a primitive notochord, a flexible rod supporting the body, emerged, laying the groundwork for the evolution of vertebrates, including ourselves. The Cambrian seas teemed with an astonishing array of bizarre and wonderful creatures, many unlike anything alive today, showcasing the incredible plasticity of life when presented with new opportunities. In essence, the Snowball Earth event and its dramatic aftermath acted as a planetary bottleneck and then a reset button. Life endured the deep freeze in scattered refugia, but it was the subsequent hothouse world, with its massive nutrient flush and resulting oxygenation of the oceans and atmosphere, that provided the perfect crucible for evolutionary innovation. The extreme environmental changes spurred an equally extreme biological response, leading to the rapid diversification of complex multicellular life that would forever transform Earth's ecosystems and lay the foundation for all subsequent animal evolution. It was a testament to both the destructive power of planetary forces and the incredible resilience and adaptability of life itself. We have journeyed through an epoch of unimaginable extremes, a time when our familiar blue marble transformed into a silent alien white sphere, only to be reborn into a vibrant, life-teeming world. But the story of Snowball Earth is not merely a historical account. It is a living scientific mystery, a dynamic field of ongoing research and passionate debate that continues to refine our understanding of planetary systems. The echoes of that ancient ice age resonate in laboratories and geological field sites across the globe, providing invaluable insights into Earth's resilience and the delicate balance of its climate. One of the most central and enduring debates within the scientific community revolves around the very extent of the glaciation itself. Was it a hard snowball, where the entire planet, from pole to pole, was encased in a solid, continuous sheet of ice, kilometers thick, with no exposed liquid water? Or was it a slush ball, a slightly less extreme scenario where some areas, perhaps a belt around the equator, retained patches of open water or very thin, fractured ice, allowing for some limited exchange between the atmosphere and the ocean? Proponents of the hard snowball model point to compelling evidence, such as the widespread distribution of glacial deposits found on every continent, including those that were situated in equatorial latitudes during the Neoproterozoic era. They argue that the sheer volume of ice required to explain these deposits suggests a truly global freeze. Furthermore, the presence of thick cap carbonates, distinctive layers of limestone and dolostone that directly overlie glacial deposits, is seen as a powerful indicator. These cap carbonates are thought to have formed rapidly from the massive influx of weathered material and dissolved carbon dioxide into the oceans immediately after the ice melted, suggesting an unprecedented atmospheric CO2 buildup that could only have occurred if the entire ocean surface was sealed off from the atmosphere for millions of years. Under a hard snowball, the hydrological cycle, the continuous movement of water on, above, and below the surface of the Earth, would have essentially ceased, locking away moisture in vast ice sheets and preventing the normal exchange of gases between the atmosphere and the oceans. This would have allowed volcanic CO2 to accumulate without being scrubbed out by rain or weathering. However, the slush ball hypothesis offers an alternative, more nuanced perspective. Scientists who favor this model acknowledge the extreme glaciation, but suggest that a narrow band of open water, or at least very thin seasonal ice, might have persisted near the equator. This belt of life would have offered crucial refugia for photosynthetic organisms, which would struggle to survive under a kilometers-thick ice sheet that blocked out almost all sunlight. The slush ball model proposes that if some open water remained, even seasonally, it could have allowed for a continuous, albeit greatly reduced hydrological cycle and a persistent, though meager, primary productivity in the oceans. This would make the survival of complex eukaryotic life, like the ancestors of animals, more plausible, as it would provide a continuous, if harsh, habitat. Evidence supporting the slush ball idea often comes from interpretations of certain sedimentary structures that might indicate wave action or less extreme anoxia in some ancient ocean basins, or from models suggesting that even with very low CO2, a complete freeze of the equator might have been physically difficult to maintain under certain solar luminosity conditions. The distinction between a hard snowball and a slush ball is not merely academic. It fundamentally impacts our understanding of the limits of planetary habitability and the resilience of life. If Earth truly became a hard snowball, it means life endured one of the most severe bottlenecks in its history, surviving in isolated, extremely limited environments like hydrothermal vents. If it was a slush ball, the pathway for evolution and survival might have been slightly less arduous, with more widespread, albeit still challenging, refugia. This debate continues to drive new research, with scientists examining subtle geochemical signatures in ancient rocks, conducting advanced climate modeling, and searching for new geological evidence that can tip the scales one way or the other. Each new discovery, each refined model, brings us closer to painting a more accurate picture of this truly alien chapter in Earth's deep past. Beyond the extent of glaciation, other areas of debate include the precise triggers for the ice ages, the exact duration of each snowball event. There were at least two major ones, the Sturtian and Marinoan glaciations, and possibly others, and the detailed mechanisms of the eventual thaw. For instance, while a drop in atmospheric CO2 is widely accepted as a primary trigger, the relative contributions of continental configuration, enhanced silicate weathering, and even potential biological innovations that might have consumed CO2 are still actively investigated. Similarly, while volcanic outgassing is the favored explanation for the thaw, the rate at which CO2 accumulated and the specific atmospheric and oceanic conditions that led to the rapid melt are subjects of ongoing detailed geochemical and modeling studies. Understanding Snowball Earth deepens our knowledge in profound ways. It dramatically illustrates Earth's resilience, showcasing the planet's capacity to recover from environmental catastrophes that dwarf any modern challenge. It reveals the Earth system not as a static, stable entity, but as a dynamic, interconnected network of geological, atmospheric, oceanic, and biological processes capable of radical transformation. The story of Snowball Earth underscores the delicate balance of our planet's climate system, emphasizing the critical role of greenhouse gases, particularly carbon dioxide, as the Earth's primary thermostat. We see how positive feedback loops, like the ice albedo effect, can quickly accelerate warming or cooling, pushing the climate system past tipping points into entirely different states. The carbon cycle, which we often take for granted as a stable, continuous process, is revealed as a fundamental control knob for planetary temperature. During Snowball Earth, the interruption of this cycle by vast ice sheets allowed CO2 to accumulate to extraordinary levels, eventually triggering a super greenhouse effect. This ancient lesson highlights how deeply intertwined the geological processes of volcanic outgassing and rock weathering are with the atmospheric composition and, consequently, the habitability of a planet. It also forces us to consider the limits of planetary habitability. Snowball Earth represents perhaps the closest our planet ever came to a truly sterile state, a stark reminder of the narrow band of conditions that allow for the flourishing of complex life. It makes us appreciate the uniqueness of Earth in the cosmos, a world that has, against incredible odds, maintained conditions suitable for life for billions of years, despite episodes of extreme environmental stress. These ancient events hold practical significance for us today, particularly as we grapple with modern climate change. While the causes and timescales of Neoproterozoic glaciations are vastly different from current human-induced warming, the underlying physics of atmospheric greenhouse gases and powerful feedback loops remain constant. Snowball Earth provides a natural laboratory for studying extreme climate sensitivity. It demonstrates that the Earth system is not infinitely buffered. It can undergo dramatic, rapid shifts when critical thresholds are crossed. The runaway ice albedo feedback that plunged Earth into a deep freeze serves as a cautionary tale about the power of positive feedback mechanisms to amplify initial changes. Today, we are witnessing the reverse. human activities are rapidly increasing atmospheric carbon dioxide concentrations, primarily through the burning of fossil fuels. This increase, though occurring over decades and centuries rather than millions of years, is pushing the climate system into uncharted territory. While we are not heading towards a hothouse of Snowball Earth proportions, the ancient story teaches us that even relatively small changes in the planet's energy balance, mediated by greenhouse gases, can have profound and long-lasting consequences. It emphasizes that Earth's capacity for self-correction, driven by geological processes like silicate weathering, operates on timescales of hundreds of thousands to millions of years, far too slow to mitigate the impacts of human-induced climate change on civilization within our lifetimes. The planet will eventually recover its balance, but the conditions during that recovery period might be utterly inhospitable to our current ecosystems and societies. Ultimately, the story of Snowball Earth is a testament to the incredible dynamism and resilience of our planet. It is a narrative of extremes, of a world repeatedly brought to the brink and then spectacularly reborn. From a vibrant blue marble teeming with early life, to a silent, frozen wasteland, and then to a superheated hothouse that paved the way for the Cambrian explosion, Earth has undergone transformations almost beyond our comprehension. This journey through deep time reminds us that the stable, temperate world we inhabit today is not a permanent fixture, but a fleeting, precious moment in Earth's long and turbulent history. It underscores the profound interconnectedness of all Earth systems, the atmosphere, oceans, land, and life itself, and the immense power of geological processes that quietly shape our world over eons. As we look up at the familiar blue sphere, perhaps now with a deeper appreciation for its complex past, we are left with a powerful message. Our planet is a living, breathing entity capable of astonishing change. The lessons from its ancient, icy past serve as a profound reminder of the delicate balance that sustains life and the responsibility we bear in understanding and preserving the unique conditions that make Earth our home. The echoes of Snowball Earth challenge us to look beyond the immediate present and consider the immense forces that have shaped and continue to shape the destiny of our extraordinary